Welcome back. So in this video we are going to do some implicit differentiation examples. These will be some mostly straightforward problems, and then I'll have some more complicated ones in another video. This is just meant to get you used to the basics of implicit differentiation. Remember, everything you know about derivatives already applies. We're just doing something slightly different because we have implicitly defined expressions. So let's get going. For this example, let's say I have x cubed minus y to the 10th equals 124. And I want us to find the derivative of y with respect to x at the point 5, 1. So to get this going, first we need to find the derivative of y with respect to x. So really this is two problems tied up in one. The first part is to find dy dx, and the second part is to substitute in the point. So let's go ahead and differentiate both sides. I'm taking the derivative with respect to x of both sides, so I just write that d dx notation there. Then I can just go through this as I normally would with a derivative. I'm just going to have something that comes up a little different with the y's. So the first term is just 3x squared using power rule. And then I'm going to use power rule again on the y. So the 10 comes in front, the power decreases to 9, and we just need to multiply by dy dx. And the reason for this is because we are technically applying chain rule. We are saying y is equal to something and that something has a bunch of x's in it, but we can't see that right now. So instead, we are just going to assume that y represents a bunch of stuff that also needs to have its derivative taken. So chain rule, we do the derivative of the outside, the 10 comes in front, the power decreases by 1, and we multiply by the derivative of the inside. This is the technical explanation for why we do this. You could really just remember that when I am doing implicit differentiation, I always need to multiply by dy dx every time I take the derivative of y. I'll try to say that multiple times throughout this video so that really sticks. Then on the right-hand side, the derivative of a constant is just 0. So we've taken the derivative now, but we need to solve for dy dx. We ultimately want to have dy dx equals so that we can evaluate it at a specific point. So what I'm going to do is add the 10y to the 9th dy dx over to the other side, and then just divide by 10y to the 9th. So really, I'm just trying to isolate the dy dx and solve for it, just like you would maybe solve for x or solve for y in a different sort of algebra problem. So there we go. I found dy dx. It's 3x squared over 10y to the 9th, and I just need to evaluate it at the point 5, 1. So I'm going to plug 5 in for x and 1 in for y and simplify. I'm getting 3 times 25 over 10. We can divide 25 and 10 by 5. That's just how I'm going to simplify the fraction. You can simplify it however you'd like. I do 25 divided by 5 is 5. 10 divided by 5 is 2. So I'm left with 15 over 2. And there we go. I've found the derivative of y with respect to x and evaluated at the specific point 5, 1. Just a comment too, if you're doing problems later that involve tangent lines, what we found here is the slope of the tangent line at the point 5, 1. So just remember, derivative is the slope of the tangent line, and we found the slope at the specific point. Okay, let's do another example. This time I'm going to have x to the 5th plus y to the 4th is equal to 3y. And I just want to ask us to find dy dx. So if you want, you could pause the video and try this out. Just remember everything you know from doing algebra problems, from doing differentiation. It all applies here. So pause now, see how far you can get, give it your best shot, and we'll come back and do it together. Okay, so in this problem, I'm trying to find the derivative of y with respect to x. There are y's all mixed up in this thing, so I'm just going to apply the derivative with respect to x of both sides and then simplify to get what I want. So let's take the derivative of both sides. So here we are asked to find the derivative with respect to x. So remember, we treat the x's normally, but with any time we take a derivative of y, we'll need to multiply by dy dx to handle the chain rule. So the x we handle normally, I do 5x to the 4th. Then with y, I have to do chain rule, so it's still 4y cubed, but then I have to multiply by dy dx. And we do a similar thing on the right-hand side, so I keep the 3 on its own, that's just the constant in front, and then I'm taking the derivative of y with respect to x. Okay, so next task is to solve for dy dx. I'm going to group all of my dy dx terms together so that I can factor it out and simplify. This is just like grouping like terms like you would do in an algebra problem. So I'm going to subtract 4y cubed dy dx over to the right-hand side. Then I'm going to factor out the dy dx. So both of the terms on the right-hand side have a dy dx in them. So I factor that out. I have dy dx times the quantity 3 minus 4y cubed. And then I just divide by that 3 minus 4y cubed to get dy dx by itself. So I'm left with dy dx equals 5x to the fourth divided by 3 minus 4y cubed. And there we go. From this point, you could plug in the values for x and y to find the derivative or the slope of the tangent line at a specific point, but this is all we were asked to do for this problem. Okay, one last example, and I will just shake things up a little bit here. Let's say that we have x times y is equal to x cubed, and let's find dy dx. So you can pause now and try this on your own. My hint is that I said x times y, so we're going to need a specific rule for that. Remember, everything you know applies that you've learned before. We're just doing a new thing where we have a function implicitly defined. Okay, so we're finding the derivative of y with respect to x, so we'll just take the derivative of both sides with respect to x. I apply the d dx to both sides, and on the derivative of x times y, I'm going to need the product rule. It's x times y. So when I do this, I take the derivative of x multiplied by y, and then I add it to x times the derivative of y, and I'll go ahead and take the derivative on the right-hand side. That's just 3x squared. Then the derivative of x is 1, and the derivative of y with respect to x is just dy dx. Now I am going to simplify and solve for dy dx. That's my ultimate goal, is to get something that says dy dx equals. So I'm going to subtract that y over to the right-hand side. I'm trying to get dy dx alone, and then I just need to divide by x in order to solve for dy dx. So my solution is 3x squared minus y all over x. And again, you could use this then to plug in a specific point and find the derivative or the slope of the tangent line at that point, and then create your tangent line from there. Okay, so those are just a few basic examples of how to use implicit differentiation. Thanks so much for watching, and I will talk to you in the next one.